Do you want to get us started, Steven?
Yeah, do a quick little intro. Well, just thanks to everyone for showing up today. We're excited to get, what is this, like the fourth year of these
Fifth
summer
year.
workshops? Fifth year? Wow, fifth year of these summer workshops. Super excited about that. And definitely in addition to Camille's machine learning text analysis expertise, we're also excited to have her start things off because she's a vet and she's done this before. So it'll help streamline this process as well. And just kind of saying, yeah, we're all coming into this from different levels of background and expertise, and that's totally okay. That's like the point of this workshop. And I think I just want to sort of emphasize that it's a very open space. Feel free to ask questions, no stress, no one's judging. This is new to all of us, except Camille. So we're all coming into it through the same perspective. So yeah, feel free to send messages in the chat to myself, to Billy, because we will run into errors eventually, just with random things that come across. Yeah, excited to get started. Billy, do you want to add anything? I probably forgot something.
No, I would just say, like Steven said, this is the fifth year that we've done this. We tried to make it as like interactive as possible so that it's not just somebody lecturing at you. There, of course, will be some lecturing that Camille and the other presenters are going to do. But ideally, what we would like is for folks to have that script open that Camille's provided and just kind of like following along, doing the problems that are provided. This is not required. We're not going to do like a homework check or anything like that. So if you're not doing that, it's fine. But it's sort of how this was designed. And it's modeled after some other very successful models. Like a Neuromatch and things like that. Just a quick background. I know we have some new names in here. Just to let you know, Steven and I are both members of the COG board who organized this whole thing. Camille is a rising sixth year PhD student at Temple. Your mouth went, you made a frown when I said that. I'm very sorry. Camille's very talented. She's an F31 fellow. She's in the social psychology program. She's currently doing a summer internship working with a bank that works with farmers. I don't know anything more specific. I'm sorry, but Camille is very brilliant, and you guys are in good hands for this specific tutorial. So yeah, if you have screen sharing ability, we are recording. You are welcome to take it away whenever you're ready, Camille.
Fantastic. Thank you. That was a very nice introduction and nicer than I expected to hear. So thank you.
Yeah,
All
it can
right.
be real mean, you know.
Yeah, I know. I was ready for a roast today. So all right. So here's our tutorial for today. I guess I'll start with this little YouTube video. I hate watching videos of myself, but I did plan this ahead of time, so we may as well do it. Let me know if you can hear it. Hey everyone, my name's Camille, and I'm going to be walking you guys through how to use tidy models in R to train some machine learning models on text data. So if you want like a more general overview of machine learning, I recommend you watch Helen's tutorial from last year. In this tutorial, we're going to go a bit more into how to train models using text data. So if you have I don't know, interview-based data or survey-based data where people used a lot of text to write whatever they wanted, and you want to predict something, some outcome based on that text data, that's what we'll be working on today. So there's two main kinds of outcomes or ways you can use these kinds of models. You can train machine learning models to be in a regression format where you're like predicting a continuous variable, which is what we're going to be doing today. Or you can use classification, which would be grouping into two groups. So that would be something more like using people's text responses to determine if they, I don't know, some group variable, if they had brown hair, blonde hair, something like that. That's probably not something you'd actually want to predict on, but something like that. Today, we're not going to be doing classification models. We're going to be doing regression models, like I said. So we're actually going to be taking reviews of coffee to see if we can predict the rating or like the score that people gave this coffee. What's cool about this sort of approach is that you can then extract which words that we saw in the reviews that are most associated with higher scores or lower scores. And then you can take that and generate insights about kind of what sort of coffee should we make next? Do people hate this kind of flavor or love this kind of flavor? These are the kinds of insights you can generate using this approach. I mentioned we're going to be using the Tidy Models framework. Tidy Models is awesome. It's like a framework, much like Tidyverse, but specifically for modeling. It's great because a lot of times when people code these different kinds of models you might want to use, like linear regression or decision trees or random forests or support vector machine, they all take different inputs in like different formats, which make it really complicated to compare and code them all. So Tidy Models is a way of, or is a framework that helps to kind of make everything consistent, the inputs consistent, the formatting consistent, and that makes it really easy to compare across different approaches because like the way you make the code is more or less the same as opposed to all being different. That'll make more sense once we get into the tutorial, but just as a heads up, that's one of the benefits of using this approach. We're going to focus a lot today on basically how to use text data to predict these models. So specifically feature engineering. So like, how do we actually take these little blurbs that people wrote and like create variables to put into our model? And then the other main thing we'll be focusing on is training a couple different models and comparing across them. So maybe you want to try like different sorts of feature engineering, something a little more complicated, something a little more simple, and see if the simple one outperforms the complicated one, something like that. Or maybe you want to try a couple different actual machine learning algorithms. So maybe you want to try something simple, like a linear support vector machine, like I talked about, or you want to try something complicated, like XGBoost is a really buzzy one right now that people talk about a lot. So again, we can compare those two algorithms and compare the approach and then decide which one is best or at least best for our needs, and save it out as a last fit and visualize some of our results and ultimately get to that insight of like, what kind of coffee is best or what kinds of products should we make in the future? Or in any kind of research setting, pulling out like what the knowledge is from your data and what features are most predictive of your outcome, basically. So I will be walking through this with you over Zoom, but of course, if you're watching this later on, feel free to email me and let me know if you have any questions. Thanks so much. Who needs a roast when you have to watch a recording of yourself? Am I right? Well, a lot of the things I'll talk about today or talked about in the video will make a lot more sense as we go along. But do I have like questions from the get, like anything that I said that didn't make sense that we want to talk about? I think the main things that I touched on were just like kind of the flow of what we're going to do today, how cool Tidy Models is as a framework, which will make more sense in practice. And I talked a little bit about regression versus the other one that I totally forgot right now. Categorization? No, whatever, doesn't matter. We're going to be doing regression today, so that's why it matters more. Okay, I was planning on just like going through in my RStudio, like and running it as we go. Is that okay? And you guys can follow along with this. This is on the GitHub, obviously. It's in the here if anyone else needs to. Oh, just kidding. Wow, that's amazing that worked.
Yeah, and I will add the link to the viewer if anybody wants to follow along that way in the chat.
Sounds good. Perfect. So in that case, I'm going to change my share to our
I will add one thing though, if anyone has any questions, just 'cause I think I ran into an issue when I was installing a package, just because I didn't have these packages installed. So if anyone runs into anything like that, like please feel free to let us know.
Cool. Love that and agree. Yeah, so first thing is loading in the packages. Obviously, like Steven kind of just said, if you don't have these installed, you'll need to install them. You know, you can use the little GUI thing over here or just like install. Oh, well, it helps install packages. Yeah, and then you put it in quotes, whatever you want to do. But I have them all installed, so I will not be doing that. So I will just run the librarying, making sure we've got them all in there. I tried to really like over comment this so that like you will never be lost. But if any of my comments ever don't make sense, just let me know. So then I'm just setting the working directory as where we are, or like where this script lives, and loading in our coffee data. So I cleaned this up a little bit ahead of time, but it has the name of the coffee, the roaster, where it was roasted, what roast it is, the rating, and the actual review. And so basically we're going to be using the review to see if we can predict the rating and generate like insights about what kind of coffee people like more than other kinds. Any issues or questions up to this point? If you need, you can also, like, I remember being a guest on these, like I was a big lurker. So if you would rather just put in the chat that you're struggling, I think Steven and Billy will help you out.
Yeah, and if you are, I don't know, uncomfortable putting it in the public, you could DM us. You could do
Yeah.
private message to one of us, and we can help you out as well.
That's a big pro tip. Love it. All right. So before we like get to the actual modeling, let's just take a look at our data, make sure it doesn't look too crazy, make sure we're like in a good spot for this kind of approach. So we take our data frame, pipe it into ggplot. Let's just make a plot of the distribution of ratings and see if we even have like a distribution at all. Maybe they're all rated 95. What would we even do then? You know? I like to use this bin width so that I like definitely get the right. Sometimes the way histograms work with like being open on the left or the right really confuses me. So if I use a bin width that's like just under 1, it gets rid of that. Anyway, I tried to pick like a very latte-y color to be like fun and on theme. So we can run, oh, and I also exclusively use theme classic. I can't really look at plots if they don't. I have a PC at my new work. And so shortcuts are like murder now because the button for shortcuts is like elsewhere. So anyway, it's like a disaster, but it's fine. Okay, so here we have our histogram of our ratings and our cute little latte color. We love it. So, you know, it's not like a tremendous distribution. There's not like a big range here. For this purpose, I'm not too worried about it, but this is the kind of thing you want to check, you know, make sure you have a distribution and that kind of thing. I also just think it's kind of cute. So it seems like for the most part, you know, they're rating these copies pretty well, like around 93. So pretty good coffee overall. We love to see it. I'm going to make a different plot that kind of just like starts to look at which words are associated with higher or lower ratings. So to do that, we're just going to unnest the tokens. This is really easy. You just pipe in the data frame and say, you know, from the review column, let's look at that. Like from this column here, I didn't mean to sort it, but you get the idea. Just like unnest all the words. So I'll show you what that looks like. Oops. Oh my God, you guys, this is going to be a struggle. These shortcuts. Okay. So now you can see that it's like in super, super long form where instead of review, we now have word. Does that make sense? Are we following what just happened? Okay. So now like each row, instead of being one review, it's one word from each review. So we can use that then. Well, yeah, we'll count all the words and sort them and take like the top 50 or so. Oh, let's just look at which words are the most common. Oh my God, it's gonna drive me nuts. So we can see that, as you often see with text data, our most common words are things like and, in, a. These are what we call stop words. If you want like more in depth, you can see my text tutorial from last year. So that's common. But then we get aroma, mouthfeel, finish, chocolate, acidity, that sort of thing, moving on. So what we'll do is say, on average, if we group by each word and take the average rating associated with each word, we can plot which words like are more or less associated with higher or lower ratings. I'm just going to filter out words that weren't used a lot. Pipe that right into ggplot, where we have number of uses on the x-axis and the rating on the y. I'm going to add a horizontal line at the mean so you can see like what's above average and what's below average. And then we can actually add, instead of like dots, you could just add words. So that way, like the only thing you're plotting is just the actual labels. I'm going to use a log scale on the x-axis because like with text data, you'll have a ton of words that are used very few and very little amount of words that are used a lot. So it kind of condenses it all down. And again, I only use Theme Classic typically. There she is. Cool. I don't know if I use the like zoom, if it'll work. I'll have to redo the share, so I'll just make it really big.
It looks pretty legible. I don't know if that.
Okay, cool. You guys can see that? Awesome. So we can see that, first of all, and, which is a word we use a lot. Let me see if I can get my little, should really practice the pointers and stuff more often. Ugh. Anyone off the top remember how to do a laser pointer on Zoom?
I didn't know you could do that.
Okay, that's okay. Can you guys see my cursor?
Yes, we can see that.
Yes.
Oh, okay, perfect. That's fine then. So you can see and is our most used word way out on the right here, but it's like it's right on the average, right? Because it's not really associated. It's not going to be used more, we would hope, for higher versus lower rated coffee. Does that make sense? That intuition, why it's like right on the line here. Whereas elegantly and star and flavor and juicy, those are all associated with better rate, or at least like on average tend to show up with better ratings. Whereas smoky raisin is not as popular of coffee, which is perhaps intuitive. I mean, I like raisins, but maybe not for coffee. Any questions about this plot or kind of just this basic like exploration of our data here? Or like how I built this plot or anything like that. I think it's cool to have just the words instead of like dots and stuff. I think it makes it look really clean, really nice.
Yeah, I think this is like a super cool way to just put a plot together, especially with the words as the labels. This is like good to know just in general. Also.
Yeah,
Could
for
I
sure.
ask? I know some folks may have used R before, but might not have used piping. That tends to come up pretty regularly. Is there anybody who's confused about the piping or maybe hasn't seen that before? Emma, I see you shaking your head. Is that a no, you haven't seen it, or?
No, I'm familiar with piping. Sorry.
Okay, no, okay, great, yeah. We do like an intro boot camp every year, and that tends to be something that pops up. So I just wanted to make sure everybody can follow along with that.
I'm obsessed with piping. I love it. And I just love the tidyverse in general.
Yeah, it is nice. It took me forever to get on the piping train, but
I remember you telling us that.
Yeah.
You're so brave. You're just trying to do something creative, just trying to be an inspirational.
Just trying to make illegible code, basically.
Yeah, that also, yeah.
Fair. I mean, piping makes code more legible. That's what I should say.
Important. Yeah, so true. I agree. Yeah. You probably had to think a lot harder to, create that super legible code. Just to overcomplicate things.
Yeah.
Anyways, so now we can get into like the actual modeling. So one of the important things to do for most machine learning approaches is to set up a data budget. And what this means is just setting aside part of the data that we are not going to use to train the model. We're only going to use to test the model and make sure it's like a good fit. And it's important to do this so that you're not like double dipping. And like, obviously, if you train a model on certain data and then you test it on that same data, it's probably going to perform awesomely because it's trained on the same thing. So we want to hold a little bit out and not at all taint our model with that data. And this also helps like allow you to like try as many things as you want to try and like not really worry about I don't know, like usually we worry about multiple comparisons and things, and I feel like this is a good way of like you can see which kinds of models are really not working, really working, like play with it a lot before you do your final fit, which is really nice and really helpful. And it's what's going to allow us to compare some of the different models we're comparing today. So if you ever want to reproduce the same like splitting again, you want to set a seed so that the like random splits of observations are like always the same. So here I set a seed, and then there's this really cool, I don't know if is it Tidy Models that has this initial split? R sample, yeah, anyway. So you can do this with initial split where you just say, here's all my data. Like I didn't use the unnested version, I'm just using the regular version that's one observation per rating. Saying out of all of these observations, make a split for me, split into testing and training data, and stratify by rating, which just means like you don't want all of your training data or all of your testing data to be like the super high ratings or the super low ratings. You want to have like a nice spread. So that's why we stratify here. I'm just using like whatever the default is for how much data goes into testing and training. But if you want to set that custom, you can also do that here. So then we make so we'll here, run our seed. Oh my God. There we go. Split our data using this initial split. And then on this split, we can sort our training data. So we're going to call that coffee train, and our testing data called coffee test. So you can now see that we've split. Yeah, that looks like math would happen. Yeah. So we have our training data has 1,500 observations, but we held out about 500 of them for our testing, which I think will make more sense. So basically, we're going to use this coffee train to like train all our models and everything. And then once we're like, for sure, we're going to use this one, then we see if it's any good on the testing data, basically. Does that make sense? Okay, I would like to close those. Hello, whatever. All right. Close them now? No? Okay, weird. And then to make even better predictions or rather like estimates of how good our models are going to do, I'm also going to create cross-validation folds. So that way we can be, it basically makes little training and testing sets within our training data that we can then run a bunch of metrics on. I don't know why I see other people who are smarter than me set another seed here. I don't know why, or if you need to. This is what the experts do. I don't know why. Someone who's smarter than me or has more time can figure out if that's necessary or not. So then we can just use this cross-validation fold and just say on our training data, make some cross-validation folds and stratify by rating again. And this will automatically make it for you. I set up here, we're going to use cross-validation folds, but you can always use bootstraps instead. I think that uses replacement. So you get more data in each fold, but it's like you're recycling the data more. So it's really up to your approach. But like you can see here that now each fold within our training, within our training data has in and of itself its own little test or training set and testing set and training set and testing set. And we'll run our models on each of those folds to give us a bunch of metrics about whether it's any good, basically. I know that's kind of a lot of information. Do we have questions? Did I lose anybody? Why can't I close these? That's okay. There we go. That's really annoying.
It's been a while since I've done training and testing. Could you just like briefly go over why we train and test?
Yeah, so like again, if you use all the data to train and then you like you're going to inflate your result when you try to like prove that it works well on that same data, because it's been like it can often overfit to like some of the quirks in that data. And it's kind of double dipping in a way of like, this data told me that these things are gonna be very predictive, and when I use it on that same data, indeed they are very predictive. I'm the best engineer in the world. But that is like not necessarily the case. So it's important to hold data out aside, because if you train this awesome model, but then you test it on data you held out and it's terrible, that's how you know you overfit your model. Does that kind of answer your question? I don't know if Stephen and Billy, if you have anything to add on why testing and training is important, but.
No, I mean, I would say that, yeah, it's something that comes up a lot in AI research and stuff, but like you could also think of it as just like existing outside of that with like any sort of a study. Like you ideally want your sample to be representative of like the larger phenomena. And if you give it only data, like any sort of an AI algorithm is going to like learn the data you give it. And so it might learn stuff that is like extremely specific to that sample, but not necessarily representative of the broader world that you actually want it to function in. So just like, yeah, like Camille said, withholding a little bit, make sure that like you can actually assess how much of that is happening, more or less. And like I said, it would be the same thing with like any research study that you want to do. You just ideally want it to be generalizable.
Perfect. Thank you guys.
Yeah, no problem. I think it like the double dipping thing really shows up a lot in neuroimaging stuff, which is not the same as this, but I think that it's a really good for building an intuition where it's like, if let's just say you have total noise because you scanned a dead salmon or something, that's a thing someone actually did. And you basically say, oh, I'm going to pick like as my predictors, all of the things that like lit up for some reason, totally based to chance. And then I'm going to predict based on that. And when I predict, or when I say like, was there activation in those spots? There sure was, because those are the only spots I picked. It was due to noise. It was totally random. There was nothing like of use there, but that's how I made this model, is based on, it'll overfit to the noise because it thinks it's finding something. Cool. I'm just looking at the chat really quick. Yes. Okay.
I think I think what Billy's saying, we just need to get that. I think the function would be, I'm gonna put it in the chat.
Yes, hang on. That should be remedied by loading tidyverse. And if you don't have it installed, then you'll need to install it.
In tidyverse, you can kind of think of it as like a wrapper that contains a lot of packages. So it might take a minute or two to load because it's installing a bunch of them. But yeah, just give that a moment and it should be fine.
That happens to me all the time when I start a new session and I think tidyverse is libraried and it's not. And then I try to run my whole code and it's like, I have no idea what a pipe is. I'm so sorry.
There's so many times there's a lot of scripts at this point that I like tidyverse is the only library I use, and I will forget to do it as the first thing. And yeah. I also I know that message very well because I forget about it.
Yes, 1000%. All right, so next we want to set up our feature engineering. So we have these splits that's just like, we have our reviews and our ratings, but how do we actually like get that into the dependent or independent and dependent variables that we're going to use, right? So feature engineering is the process of creating features or input variables for your machine learning model. In this context, we're going to create features from text data using techniques like tokenization, which you kind of saw before, just basically taking chunks of text and splitting them into little tokens. And TF-IDF, or TF and TF-IDF, which is term frequency and term frequency inverse document frequency, which I'll explain a little more in a second. and normalization. And later on, we'll compare these approaches to see which one performs best. So like, again, this is just 3 different ways I thought of to like create our feature engineering for these models. You probably might only have one idea and then you want to try another one, or maybe you don't want to try anything else. You like to make a model, you only need one of these, but I just thought it'd be interesting to kind of compare some different approaches. So basically we're saying we're making a recipe, which is part of like the tidy models framework. That's saying basically our recipe is going to be, we're going to predict rating based on what's currently in the review column. So this is just like I bet many of you have run like just a regular linear regression, like an LM model in R, and you might be used to seeing this sort of notation where you have the thing you're predicting and then the tilde and then everything you want to predict with. So that's the same thing here. We're using the data that's currently in the review column to predict the rating column using our training data. So what's very cool about tidy models, and I think this is from tidy text or text recipes, excuse me, is like the RStudio team has like developed all these super cool steps to add to recipes. So we can just add step tokenize, which is going to tokenize all those reviews. And then we can do a token filter, which is just going to filter the top 500 tokens, or you can set that to whatever you want. You could set it to 1,000, you could set it to 200, you could do whatever. And then there's one called step TF-IDF, and that's going to calculate the term frequency inverse document frequency for each item. I probably should have started with one that's just, so this is the same thing. You know, we have our model formula. We're going to tokenize it. We're going to filter the 500 most used words. And then this is step term frequency. So what that's basically going to do is calculate the term frequency. So like, did this word appear in the frequency of that word appearing in the document for each one. So basically you would be predicting rating based on whether the word, whatever it was, raisin appeared, the frequency that the word raisin appeared in the document you're using or in the observation. So that's fine. What's cool about inverse document frequency is it's the term frequency multiplied by the inverse document frequency, which is the amount, or like 1 over the amount that it shows up in every single document. So which basically all that it really means is that it like punishes or reduces down words that show up a lot. So this approach is very similar, but it'll leave only the words that are like kind of unique at the top, and words like "and" that show up in every single review will be kind of reduced down to 0. That was kind of a lot of math, but if does anyone have follow-up questions about that? These are 2 like, you'll see both of these term frequency and TF-IDF used a lot in like text-based analyses. But what's cool about TD-IDF, like reducing down words that show up in every document or punishing words that show up in every document, is that it kind of addresses stop words without needing to actually remove stop words, which is cool. Or like if there's a pattern that's like that includes stop words, it's really interesting. Like for some reason, the word "I" shows up in all the good coffees. Like maybe that's something we want to capture. TF-IDF would kind of allow for that if I wasn't showing up in all the documents, if that makes sense.
And sorry, Camille, could I ask, so
Yeah.
with something like that, it's pretty much just going off of the frequency like dimension, right? It's not, so like if you had, I guess like, I think this is basically the example you're just saying, but like, yeah, if like it's a coffee review and the word ground or something pops up a lot just because it's a coffee review and they're just talking about grounding coffee a lot, would that then maybe be affected by this, even if like you didn't want it to be? Or
right, so
like
basically
if you were trying to target stop words, could it potentially get mixed in with those stop words?
Yeah, so basically like in this version where we're just using term frequency, a lot of your predictions are going to be really hot. Like the word "and" is going to have really high term frequency.
Right.
But maybe that's like not what we think will be most predictive. So in this version, the word "and" is going to have way lower values than it would in the term frequency one, because it's like basically been reduced. If it showed up in every document, it would be reduced down to 0. Does that make
Mhm.
sense?
Yeah, okay.
I should have brushed up on like the specific math, but like it's 1 over the term frequency or the something such that like if it's in every document, I think it reduces all the way down to 0.
Okay.
Yes. Okay. So those are like really simple ones where we're basically just splitting everything into individual words, taking the top 500 words and calculating like our variables, like our numbers basically. So then I also made one that's like kind of a little more over the top. So we tokenize this one. We're going to, there's something called step stop words. We're also going to take out stop words, which is like really nice and convenient. We're still going to token filter. We still have TF-IDF, and we're also going to normalize all predictors. And I thought this was a useful one because it's like really easy. You don't have to normalize your predictors by hand. You can literally just add this step normalize and say, you could even say like, use something in here to not normalize everything if you just want to normalize some. But I just thought like, even though I wouldn't necessarily recommend or not recommend that for this approach, like I wanted to share this one because it's like probably a useful one for your use cases in the future. So basically the point of this section is to say that tidy models is really cool. They have like 1 million steps you can add to recipes. Basically anything you could think of that you want to like be a part of your workflow, you can add to these recipes, which is really nice for like visibility and transparency and knowing exactly what you did to your data before putting it into your model. So basically what we're going to do is compare like, does the TF-IDF perform better than the TF one? Does the super complicated one where I also like took out stop words and added normalization and all this extra stuff, does that perform better or not? These are the kinds of things you can compare. So just to make sure that these are looking how we want to, you can also bake them without like actually fitting them to the data. Oops, oh my God. Oh, well, it helps to run it first, what they tell me. All right. So if we prep and then bake, we can see that we now have basically for each observation, we still have the rating, but now we have the term frequency. For this one, yeah, sorry, for this one, we now have the term frequency, inverse document frequency for the word A, the word accessible, the word acidity, the word agave, for each and every observation or for each and every review. Does that make sense? So you can kind of see that like what you set up actually worked. Like it split everything into words, and for each observation, it calculated the term frequency, inverse document frequency. So let's do that for the term frequency. For the term frequency one. So you can see for this one, instead of like percent or decimals, it's like A showed up in this observation 1 time. That's the term frequency. A showed up in this document 2 times. That's the term frequency for that document. Does that make sense? Whereas like the TF-IDF one, you'll see like a lot of these have been reduced down to almost 0 because they show up in like most of the observations. Hopefully that also kind of gives an intuition. And then this one probably look even more different. Yeah, because now everything's been normalized. So it's like been subtracted and centered on 0 and stuff. Cool. Any questions about recipes? So this is not actually running the model at all. This is just saying this is how we're going to set up what the formula for the model is and how we're going to make how we're going to engineer our features or how we're going to make our predicting variables and the things we're going to do to them before we actually run our models. Any questions there?
So, in terms of like recipes and baking and prepping, would you effectively compare it? Would you say it's like similar to pre-processing?
Mm-hmm.
Effectively, like pre-processing your data, getting it into the structure that you want it to, so that you can actually feed it into this model. Is
Yes.
that right? Okay.
I think that's a great way to think of it. Yeah, absolutely. And it's nice then because you have this little recipe that you can then use to show like exactly what you did to your data before you actually ran it through the model. And most importantly, you can compare like, are all these steps necessary? Does it actually help our model or not? That sort of thing.
Oh, sorry. And then so the one other thing I have, it looks like the product, like the thing that you are saving, it's a tibble. Is that correct? It's not like a data frame or, oh,
Yeah,
okay.
I think it's like its own kind of object. Like you have, I think like,
Right.
let's see what this makes. I'm just curious. So that's now like a data frame or
Data
tibble or
frame.
whatever.
Okay.
So actually like baking it makes it, but other like recipes I think are their own kind of objects.
Right. Okay. That's good to know. Okay.
Okay.
Which also, if for those new to R, how you like structure things can change dramatically what you can do to them. Like a matrix and a data frame might sound very similar, and they are in a lot of ways, but like there's additional features of a data frame that aren't present in a matrix, even though they're both just two-dimensional, basically spreadsheets of numbers.
All right. Any other questions or thoughts before we move on? All right, so next, also I'm not really monitoring the chat, so I'm just trusting my
We
dear
got
friend
you.
Billy and Steven to monitor the chat for me. Okay, so next let's actually set up our model specifications. I'll read what I wrote since past Camille probably thought this was worth sharing. When working with machine learning, you might want to try different types of models to find one that works best for your specific use case. Here we're creating model specifications for 3 popular algorithms. Linear support vector machine, random forests, and XGBoost. Each has its strengths and can be suitable for different types of data and problems. We're using the regression mode for all of these since we're predicting a continuous outcome, but many models have a classification mode for categorical predictions. Classification is the word I forgot earlier. Note, we're going to use the default for all of these models, but in practice, you should absolutely tune important parameters. If you want me to help you with that in the future, you can totally reach out to me. But even probably better than learning from me is learning from one of the engineers of posits, who I actually linked an example from her. She is, needless to say, much better at this than I. So definitely check out her tutorials, and this one in particular, I guess I looked into as a good example of how to tune parameters. So this is like the magic of tidy models, is that typically the way the people who engineered all of these different model types, I don't know if you've ever tried to run a linear regression model and then some other kind of model, I don't know, linear mixed effects might be a slightly different kind of format, or that's probably not true. But anyway, there's different models. The way the engineers make them, they all different kinds of formats, all different kinds of, things they take. So, tidy models was really the engineers, or the people who work at Posit being let's make this streamlined so that it's the same format, no matter what model you want to run, which is fantastic. If you want a deep dive, I also linked somewhere on the GitHub the tidy models textbook, which I know textbook reading is not a particularly, doesn't sound that fun, but it's actually really well written and I really enjoyed reading it. So all we have to do is say, I'm going to make this specification called support vector machine specification. I'm going to use the SVM linear model, and I'm setting the mode to regression. So again, for models that have a classification, you would just change it to classification if that's the kind of model you wanted to do. Usually if you can, again, usually these have arguments in here like trees equals, whatever, something, I don't know. And you can certainly tune those kinds of things. It would be trees equals tune. And that's a whole other process. But for today, I'm just going to use all the defaults because that's just not the thing I wanted to teach everybody today. So this is just setting up our specification for all 3 types of models. Support vector machines, a linear one that's usually really good for text data. Random forest might be okay. I see it used relatively often for text data. And then XGBoost, if you're looking at the data science Reddit, people are it's unbeatable. It's the only one that works. So anyway, I just thought I'd put it in there for fun. So there's our specifications. And now basically we'll put together our pre-processing recipe as Billy kind of aligned it, or like the idea is kind of similar to pre-processing, with our model specification into a workflow. So I gave an example of how you would set up like one workflow. So you could say, I'm going to create an SVM workflow that's basically the recipe and the specification together. Easy. Got it? But the other cool thing you can do that we're going to actually use is set up a workflow set. We're basically going to say, here's all of our recipes and here's all of our specifications, run them all, and we'll figure out which one's best from there, which is pretty cool. So you could, if you wanted to, also just like do a couple lines of this if you wanted. But basically here I'm saying I'm going to make an object called coffee models. It's going to be a workflow set. And so I'm saying basically, oh, it actually is literally called pre-processing. Love that. So my pre-processing, I'm listing my TF-IDF recipe, my TF recipe, and my stop words and normed TF-IDF recipe. And I'm just giving them little labels here. These don't matter. You could call them turtle 1, turtle 2, whatever you want to call it, doesn't matter. But this, you have to call whatever you called it ahead. So this is just setting up, these are the pre-processing recipes we want to use. Here's our model specifications we want to use. And cross equals true just means like, I don't necessarily want the first one to only be lined up with the first one of these. It's like, I actually want you to do all the options, if that makes sense. So then we create our workflow set with that. Does anyone have any questions about workflow sets besides them being awesome? So now you can see, yeah, this is not running it, right? Is it? No, it's still going. No, it's fine. Hang on. Yeah, so this just sets it up and it's not actually fitting it yet, right? Yeah. Yes. Okay, cool. This is where everything is later. Got it. So this is just showing us that we now have the TF IDF, the simple one with support vector machine, that one with the random forest, that one with the XG boost, and then we have our term frequency with each one, and then we have our like more complicated one with each one. So now we have 9 total models we're going to try. Does that make sense how we got there? Cool. Any questions about workflow sets? Or like how to design a recipe and a specification into a workflow? Go ahead.
Yeah, no, I have a quick question. I'm definitely new to machine learning, and the like structure of the code makes sense, which is awesome. It's just like, could you say like maybe 1 degree more of like, are we just testing 3 different classification strategies like linear, support vector machine? It's just like because the R people made the code, so like they're doing a lot of under the hood, like you can't see the under the hood
Right.
stuff. So it's like, could you just talk maybe like a little bit more about what those differences? Doesn't have to be super stats heavy, but just like in case other people are feeling similar about that.
Totally. So these are just different algorithms or like different fancy math that we can use to take to just no matter what your predictors and your outcome variable is, like there's lots of different math you can use to get.
Yeah.
So support vector machine is one that's a linear one. So it's like in that sense, it can look, it has a lot of the same benefits as like a linear regression model because it is linear. So a lot of our predictions are linear, and that helps keep things pretty easy. Random forests uses trees. I'm not really like that good at the math there. And then XG boost is like a super specialina type of boosted trees type model, which is even more fancy math than I think I will ever hope to really understand at this stage. But there's so many different kinds of models. You can Google or frankly use ChatGPT to tell you about like which ones are good for text data, which ones are good for like your use case. You can also like you can totally do this for regular linear regression. I think it's probably just that.
Gotcha.
Probably. Or whatever other model you want to do and maybe have used in the past. This is just like so you could probably look at probably the Tidy Models textbook would give you a lot of different examples of models to use, but basically these are all just different kinds of fancy math that someone has invented and thinks is a good way to, take your predictor variables and come up with an output.
Awesome. Yeah, thanks, Camille. And the way that you're able to just test which classification approach will work best is like super awesome and flexible. It's super cool how you set it up.
Yeah, exactly. And you can set up as many as you want or whatever. And we'll see how it actually looks when it runs.
Awesome. Thank you.
No problem. So now we'll actually evaluate them. And this is where we're actually fitting, or where we're actually like asking the computer to use the fancy math on our data to try to make predictions. So evaluating different models involves fitting them to the training data and then assessing the performance using our cross-validation fold. So using our training within our training data and then our little testing data within our training data to see how things are performing. Fit resamples trains the model on the training portion of each resample and evaluates it on testing portions, which is great. We're going to use this parallel. Oh, you'll probably need to install this do parallel if you didn't already. I probably should have put that up in the library section, but since we only use it once, I'm like, just have it like this. This just, these sorts of things take a while. Specifically if you, or especially if you have a lot of them or a lot of data or whatever, particularly people with a lot more data than we have here. So it's useful to make it go faster. So here we're gonna use this control resamples to basically say we want to save our predictions. I'm not as well versed in exactly what that does, but again, this is what it needs to make sure we save out all of the predictions that we can use later to see how it worked. Here's an example of just fitting one model at a time. So I could say like, I want all the resamples and all the results for this support vector machine where I'm going to use fit resamples on the SVM workflow using our coffee folds and our control prediction thing that I set up here. That would be how we do one, but you can see that running it on the whole workflow set is basically just as short, which is pretty cool. So here we're saying our coffee resamples are going to be our coffee models, which is our workflow set we put up here. Using fit resamples and our folds and save out the predictions. And I want to use the metrics RMSE and R squared, which is the root mean squared error and R squared. Which we'll look at a little bit later. So this is what's actually going to run the models. So this will take a second. I have it like in another window as well, but it would be also a good place to pause and see if we have any questions at this point. If not, I can move to my other one. I don't think it'll take that long, but
Yeah, I mean, it is surprising how quickly all the other stuff has run already. I know
yeah,
sometimes this can take a while to run in Python. So.
yeah, for sure. In the past, it's only a couple minutes, but when we're on something like this, sometimes that can feel like forever.
Yeah. And I should also ask, maybe whether or not anybody is unfamiliar with like the computing concept of parallel processing. It's not specific to R or Python. It happens in a lot of languages, but I can just like quickly mention that like when you give a computer commands, it will often do them sequentially, one right after the other. And that can take a while, given that there's other resources that the computer can use to get those tasks done. So you can kind of think of parallel processing as like multitasking, where it's doing multiple things simultaneously so that you can get it done quicker, which might not matter for like really simple things, but like Camille was saying with like this, with AI, like it'll have to evaluate thousands of stimuli or whatever, and that can take a long time. So if you have it do that simultaneously, concurrently, then you like cut down the time a lot, which is nice. It happens a lot in neuroscience. I remember the first data set that I needed to pre-process was going to take 30 days of continuous analysis. And then I found out parallel processing was the thing, and it was done in like a day. So, something to keep in mind.
Cool. It's still running, so I'm going to go ahead in the other window. So basically now that it's fitted, although it's still kind of, actually it just finished, which is cool. So that was only really a minute or two, which is really actually pretty fast. But we'll continue to work from this window. So to compare these models, we can collect the metrics. So we can, and it's literally called collect metrics, which is very cool. So this lists all of our different kinds we have here, all of our different models. And we have 9 of them, and then it brought both the RMSE and the R squared for each one, which is why we have 18 rows here. Yeah, rows here. And so it's actually sorting them. I think at this point, it's sorting them based on RMSE, I think. Yeah. Anyway, so we can see like all of the different models we have, and most importantly, you know, we have like which model it actually was and that sort of thing. But these are just numbers, which are probably not all that useful to, or like not as cool as the plot. So we can use this thing called auto plot to make a plot of how each of these performed. And actually, let me see if it's like, I don't know if classic's actually the right approach for these kinds of panels and stuff, but I just hate that gray background. It just like makes me sad. Yeah, I like that. Okay. So this actually ranks them, or like it puts them in order of like which one performed best, more or less. So here we can see in the RMSE panel. Let me move this. Nope, it's not what I wanted. Okay. So the model with the lowest mean squared error, which basically means like all the predictions are as close as possible to the actual values that we are comparing them against. Like there's very little discrepancy between the predictions and the actual values. So it seems like actually one of the support vector machine learning ones actually performed best. It's this little blue dot down here. And then all of the random forest ones, kind of irrespective of what recipe we used. And then all of the XGBoost ones, and then terrible were the remaining support linear or support vector machine ones, which is kind of interesting. Does everyone follow what I just said for the mean squared error for this plot over here? And then R squared is basically more so a measure of like how much of our data is explained by the predictors that we have in the model. So again, we see that the support vector machine, whichever recipe this is, did really well. And then all 3 random forest models, regardless of the pre-processing recipe, performed really well. And then slightly worse is the XGBoost, and then terrible are these 2 other support vector machine with the different pre-processing recipes. So that's like kind of fascinating that like, it's interesting that like the pre-processing recipe didn't really matter for random forest and boosted trees, but for the support vector machine, it like really mattered. Does that make sense what I'm saying? Like, is everyone following the logic there? Or at least like what we found, I guess. So that's cool. So then what we can do is we can rank our results based on root mean squared error or based on R squared. So if we sort this way. So in this one, we see our support vector machine learning came up on top, which is what we see in this blue dot in the plot. And it looks like in that one, the more complicated recipe was actually necessary for that one. So like the normalization and the removing stop words, but still using TF IDF and removing stop words was like super necessary for the support vector machine to perform well. Does that make sense what I'm saying? Okay. Whereas then the next 3 are these random forest models, and it didn't really matter. Like the normed and stop words one did slightly better, but like not really, as you can see these green dots here. So interesting, cool. We can also rank by R squared. And as we can see with like this green dot being a little bit above the blue dot, the best one is actually the random forest that had the stop words removed and the normalization and all that stuff. But like not that different from the others as well. So, you know, now at this point, one thing you can do is like pick the best, the very best, if that's what you want. Or like within a margin of error, you can be like, I'd prefer to pick the more simple or the more explainable model that's like performing relatively well. So for this, for example, I think I'll choose our best performing support vector machine because linear models are kind of nice and explainable, or at least like a little more simplistic in the kinds of assumptions we need to understand about them to like really be able to interpret them. But yeah, cool. When you like, you can basically do the same thing for tuning where you tune all the parameters. And when you're tuning, there's actually something called like select best, where you just pick the best one. Or you can say like select best by, which is like, it'll pick the best one within a range of your metrics. That's actually like the most parsimonious or like most simplistic, but still well-performing model, which is also very cool. But that's only for tuning. We can't do that for this, but we can still pick the best one. So it looks like we're going to go with our best performing model being this blue dot, the support vector machine that included stop words removed, TF-IDF, and normalizing all variables. If you wanted to go back and create different recipes and different like combinations of things, now would be the time, like before we do the last fit. But if we're feeling sure and we're feeling ready, this is our model, we're ready to taint the testing or the testing data with this solution, we can move on. But does anyone have any questions about like how we found out which one was best and like what RMSE or R squared means or anything like that? Cool. Sounds good. So now we can do our final fit. So let's select the best workflow for reducing error and make it our final workflow. The last fit function fits the final model on the training data, and then evaluates it on the test data. You only want to touch the test data once, so only use it when you're really sure. Again, if you want to try other things like, oh, maybe let's try that stopped word norm version with no normalization, but term frequency instead, or like some other combination, like go back and do that at this stage, not after. But once we're totally sure, we can create our final workflow, which as I showed you above is just like, you just use workflow, the recipe, the pre-processing recipe you want to use, and the model specification you want to use. So we're just saying the one that worked best was our TF-IDF stop norm. Oops, sorry. The one that's best for RMSE was our TF-IDF stop norm recipe with our SVM specification. And then we can use this last fit function to take our final workflow and fit it on the overall split. So this is now touching our test data, if that makes sense.
Camille,
could I go ahead.
Interrupt you real quick? There's a question in the chat Tejri asked
sure.
that I think you'd probably be the best person to answer. They ask, why would you need to explore other recipes before moving on, just to confirm comparisons or for some other purpose?
Great question. You don't have to, like, if you feel really good about how this model looks that we're picking, like you're fine. But you really don't want to, I think, because once again, if you try a bunch of models on the test data, like you could end up picking the one that like is kind of overfitting or like is kind of being swayed by quirks in the data. And so the kind of discipline has said we really only touch the testing data once. We try not to like use it a lot to taint our view of like how we build these models. So that's why we have our cross-validation folds and we make all those little trainee testy splits, is to try it over and over again and check as many times as we want, like which model is the one we want to use. And then we only want to do a last fit one time. Like that's something I've internalized through what I've learned, and I'm willing to accept it. And also like the super intricacies of the why are probably beyond my mathematical understanding, but it's like an intuitional understanding that like, again, we don't want to double dip and we don't want to like overfit. So I'm willing to just kind of follow along and make sure that I'm not dipping into our testing data more than once.
Would doing the final fit more than once, do you think like that would be analogous to like p-hacking, like getting to the end being like, oh, this isn't what I wanted, let me tweak this and then do it again or whatever? Or
Yeah, it
different?
like through social context clues, it seems to have the same reaction among people who are smarter than me.
Okay.
Of like, yeah, definitely don't do that.
Okay.
And people seem to be very, yeah, like you save that data, that testing data for the very, very, very end, and you don't touch it more than once. Which it seems like in practice, like challenging, like you make this whole model, you know, everyone signs off on it and you fit it last, and then like someone somewhere is like, no, change it again. And it's like, well, you know, I don't know what you really do in that scenario. I haven't actually come across that, but at least that's like what people say. And maybe if I reread the textbook, I'll have a little more insight, but it's been a while since I read it. But surely more detail is in those books.
Okay, thank you. Sorry for interrupting.
No, that was a great question. And I do think that's like kind of the beauty of saving this testing data out is like you can feel relieved knowing you're not really p-hacking as long as you're like futzing with the model with only your training set. Because you've saved your like final test for the end, and that data has not in any way like tainted, you know, how you're building your model at all. Which is nice for someone like me who wants to try a billion things and then it comes across very p-hacky, you know, or like multiple comparisons nightmare, but I just want to try it all, you know, I want to know what works best. So that's kind of one of the benefits of this approach as well. So since, you know, none of us are doing our dissertations on coffee that I'm aware of, we're okay to do our last fit today. If we change it again, it will survive. It's not like this project is super crucial for anybody. So we'll go ahead and do our last fit today. Did I run that? There it goes. So that hopefully won't take too long. Yep, there it goes, very fast. And then we'll collect our metrics for that final fit. So we see that our RMSE is 0.9, which as we know, I think that's in units of our outcome variable. So since it was like 95, 96 as our ratings, that basically means like the error is like kind of within 1 point in either direction, which is not bad at all, in my opinion. And then the R squared is 0.64. So more or less, we're able to explain about 65% of the variance in rating based on these words in this model, which is, I think, pretty good. Does anyone have questions about RMSE and R squared? This is where you'd see if you really overfit your data. Like these are very similar to how this model performed on the training data. It actually performed a little better. Not in terms of RMSE, but in terms of R squared, it performed even a touch better. I mean, within actual margins of error, it's probably exactly the same. But anyway, so that's a good sign that we didn't overfit to like quirks in the training data. Does that make sense? That intuition there? Cool. So that's awesome. This is definitely where you would see that if that was something you had done. So now let's visualize our results. So what we can do is we can extract our workflow from our final fitted model. And it's my understanding that you can do all kinds of things with these. Again, you can watch the videos I've linked and read the textbooks I've linked if you want more examples, but you can do all kinds of things with this. So we can actually tidy this workflow, which kind of converts all the model, like the whole thing, into a tidy format. We're going to filter out the intercept term. We don't really need that. And then we're going to group by whether the estimate is in the positive or the negative direction. And take our top 15 terms with the highest absolute estimates. I'm just going to clean up the names as you guys saw. Oh, that's in a different one, but like each predictor has this like TF IDF review thing in front of it. So we'll remove that and then pipe that into a plot where we have the estimate or like the coefficient on the x-axis, and then the term on the y-axis, and we're going to group that within like whether that like the estimate direction. Yeah, and like pick different colors based on whether it's predicting in the good direction or the bad direction. This will make more sense when you see it. Okay. And we're gonna make columns. And again, I picked some like coffee-y colors to be on theme and add some labels that help it make sense. Anyway, okay. So here we can see which predictors were most important for pushing the ratings in a positive or a negative direction. So we see that higher ratings are more predicted by words like viscous, syrupy, rich, floral, juicy, bright, vibrant, etc. And lower ratings are more predicted by words like drying, bittersweet, smoky, wood, that kind of thing. So my last and final parting words is that if I worked for this company, I might recommend avoiding these kinds of woody notes in the future. They seem to not be performing so well, and leaning more on the juicy, syrupy, bright flavors. Those seem to be performing a little bit better. So that's it. What questions can I answer? Yay, thank you.
Yeah, I wouldn't have guessed that like the thickness of the liquid like is most important for coffee, but I also don't drink coffee, so I don't know.
Yeah. I mean, I guess like watery coffee, like no one wants that, you know.
I suppose, yeah. And I do associate like syrupy with sort of richness or whatever, so that's
yeah. I think it's also interesting that like a lot of these words are like like cedar, smoky, wood, fir, all feel like very, like related. They're just not so good with the woody notes. Not popular.
Yeah, I just want to say this is so cool, and like the workflow, the way you laid it out was super straightforward and like easier for someone who like again hasn't worked with machine learning to be able to digest and follow along. This is super helpful.
Awesome. Yeah, I love doing it.
yeah.
I love the spot. I love the colors I picked. That's my favorite part.
Well,
I
was
worked
gonna
so
say,
hard.
if anybody else finds themselves having like interested in a similar question, I think that you laid this out really nicely so that you could just kind of swap in new data and maybe change the colors away from something coffee, something on brand with what you're studying, and then basically use the same workflow, which is really nice.
Yeah, good. I'm glad.
Yeah,
if you ever see custom hex codes in my ggplots, I probably spent more time than I should have picking out that hex code.
Yeah, there's a lot of really good websites that I go to because I'm terrible with like once there's so many colors needed, finding like good colors in a theme, and I'll just like randomly click generate until I find like a pattern or a theme that I think looks nice. And then it's just all hex codes.
I do really quickly. So I just want to say like this workshop was super helpful for like more the analytical side of text analysis, but I do want to plug Camille's old workshop. That was more like sort of navigating, loading in text, cleaning text before analysis, visualizing the text because I think that would be super helpful. And also want to plug Helen's workshop, which is more just machine learning kind of in general. And I think like this workshop right now is like a bridge between those two spaces, but for anyone interested in either or, that may be helpful to check out. And it's cool that we're getting a little text analysis repository on the COG group. And people seem interested in machine learning as well. So hopefully you'll have more of that too.
Yeah, the last thing I'm going to say, because I want to try to encourage people to ask questions, is just acknowledging too that like Steven said, we have sort of precursors, or at least spiritual precursors to this workshop available there. Every year we try to find workshops that build upon things that we've already done. We try not to repeat things that we've already done. So if this is like your first time attending something like this and you felt like maybe there were some precursors you needed. Definitely check out previous workshops. I mean, they go back to 2020. But we started off, I think, pretty basic, and I'm pretty excited. We're getting much more advanced now. But yeah, if you did wind up feeling like you had trouble following something specific or anything like that, we have all the resources there. We have recordings of these on YouTube. We have the notebook viewers available. We have all that stuff there. So,
I had a question in the chat that I just saw. Okay, yeah, so RMSE and R squared, these are like really important, and I'm happy to share more about them. So root mean squared error is basically like an additive measure of all of the error that our model or that our predictions were off from their actual values. So like what's cool is with testing and training and doing these different models, especially in our cross-validation folds, is like the model will train itself on the training data, and then it can make predictions on the testing data, like ignoring what the actual score was. So basically, if we have like it trained on a bunch of observations, and then we feed it that little training set, especially the one that's like in the cross-validation folds, and we'll be like, oh, this one had the word whatever and this and syrupy and blah, blah, blah. Based on the model we're building right now, what would the prediction be? And let's say it's 96. But then we can compare that with the actual rating given for that observation, which is 92. So the error between those two observations is 4 points, right? And we can do that for each observation in the in your training set. And then RMSE is like a root mean squared, I don't know the math. Like I know what the words mean, but I don't know the math off the top of my head. But basically it's a way to summarize, how many of like, did we get a bunch of 4s? Did we get a bunch of 0s? Like, were we perfectly on the money? Like how much error is there between our predictions and the actual values? So if that number is really high, so like, for example, our data only ranged from like the high 80s to the mid 90s. If our root mean squared error was like 10, that would mean that like our predictions were like kind of way off and like off on the scale of like the whole data, which would be pretty terrible. But in this model, for both like our metrics that we got from the cross-validation folds and then from our final fit, our root mean squared error was only like 0.9. So like a little bit under 1 point, which means that like the predictions, if the actual value is 96, the prediction might have been like 95. And like, I can live with that. I mean, it's for this data, since it was a little truncated, like it's not great, but it's fine. It's not 10, which would have been horrible. So that's the interpretation for root mean squared error. And R squared is how much of the variance in this data is explained by what we put into the model. So the fact that 65% of the variance was like explained by the words used, like, I think that's pretty good. I feel pretty good about that. There's certainly like still very important models that represent only a very small amount of the variance in certain things, and like that's totally fine. So again, it's up to you what's more important, like how much of this variability is explained by your model, or how off your predictions were from the actual. And when you're doing a classification model, just by the way, you use different metrics, obviously, because it's not like how far you are off on like a point scale. It's more like, did you guess the right group or did you guess the wrong group? And there's different metrics for that, which I can walk you through if you ever need to do a classification model. But yeah, for regression models, we use those two, the error and the basically explained, like variance explained by the model. Does that make sense, Tej? Did I do an okay job? Do they use other regression metrics? I don't know. I feel like there's one more I could use off the top of my head. Maybe accuracy. Yeah, no, that's just kidding. That's for classification. I don't remember off the top of my head. I think RMSE and R squared are the ones most commonly used. Do you, Billy or Steven, know any others for regression models off the top of your head?
I'm sorry,
don't off the top of my head.
my dog peed on the hardwood floor, so I ran to clean that up really quickly.
That's okay.
So I missed what you said, but I don't think so. I'm pretty I'm a novice when it comes to like AI and ML stuff like that. So
No problem. Yeah, and then I think off the top of my head for classification, it's like accuracy, specificity. You're basically looking at, it's kind of like a signal detection theory of like how many how many of your positive predictions are actually positive predictions, how many of your negative predictions are actually negative predictions, that kind of thing. It's a different set of metrics.
Does anyone else have any questions before we wrap up? I will say we'll work on getting this recording up on the GitHub page sometime soon, so definitely feel free to check it out. It'll be everything we just went through if anyone wants to go back and review that.
Very available. Sorry, if people want to email me or set up time to talk, happy to do whatever I can. But the YouTube videos or like the tutorials I linked and the textbooks I linked are for sure better, but you can talk to me if that is preferable for some reason.
I also do want to plug next week's workshop. Like in the messages, we'll have a workshop every Wednesday from 1 to 3 until August 7th. Next week's workshop is going to be Melanie leading us through a representational similarity analysis. So that'll be super exciting.
Which we do have previous workshops on RSA in MATLAB and Python, I think. But if I'm not mistaken, Melanie is doing hers in R, which is super exciting because R is a great tool to do that in. That's how I've always done my RSA analyses, but it's not the standard. And yeah, so I don't know if people want that. Is there a listserv? We do have a listserv. Slack is the best place to use it. But when Haroon first started this group like 5 years ago, he created a listserv, and I don't know who has access to it. I will have to figure that out. And we will hopefully send out an email notification for it.
But there is a Slack, or not Slack. There's a Slack for this.
Sorry, yeah. That was in the question. Yeah, so Slack is right now the best place to get updates. If you go onto our website, which I will link here, we do have basically every way that you could possibly keep updated on like events that we're running and things like that. We have our email, our Slack. The Google group is the listserv that I'm referring to. I just need to figure out who currently has access to it.
I put Tej the link to join the Slack in our general channel for the SDN lab, but I'm just going to send it to you directly.
You also put that in the chat, please, Camille. I was trying to find it, but I can't find it.
Absolutely, I can.
Thank you for doing that.
I mean, hopefully it's right.
Amazing.
I think that's it. And you can also Slack me on there directly if you get added to it, if that's better than emailing me.
Oh yeah, so before we let it go, any other questions, any other concerns, anything at all for Camille or for Steven or myself?
One more time, thank you, Camille. We appreciate you and your time doing this. I know you're busy as it is.
Yep, but it's fun. I'm glad. I'm always happy to help. And yeah, I'm here if anyone has any questions.
Cool.
All right, cool. All right, thank you everybody for coming.
Bye, everyone.
Bye.
Thank you. Bye.
Bye.
All right.